Everyone's here. Everyone's happy. It's February the 27th. This is my half birthday. 43 and a half today. You guys can say happy half birthday if you want. You don't have to, though. What are we doing? Chapter 9 this week. We have hypothesis testing, which is a very interesting topic. And it turns out that hypothesis testing is very closely related to and actually can be performed in most cases by doing confidence intervals. So what we learned last week is really the same thing as what we're doing this week, although it might not appear to be the same because the details are a little bit different. And if you go over here to the Blackboard Learn page for weeks 8 and 9, you'll see this funny video about Teddy's story joint that kind of illustrates what's going on. And has anybody watched this yet? No one's watched it yet. Do you want to watch it right now, or should you? Because it's kind of funny, but I don't want to. Yeah, okay, let's watch it. Life as we know it. Well, I've told you before, we're telling the same story over and over and over again. And if we're doing hypothesis testing or we're doing confidence intervals, it's kind of like Harry Potter versus Star Wars. I mean, Harry wears glasses, right? That's really the only difference. The details, of course, are different, but general plot, all that stuff is basically the same. And it turns out there's a very interesting book called The Hero of a Thousand Faces or something like that by Joseph Campbell that says all stories that are popular and people connect with across cultures and around the world are really the same story. And so if you want to write a story, you should read that book first. If you want your story to be popular anyway. There's certain things that you need to put into it. So hypothesis testing, what is it? We have what's called a null hypothesis, which says something that is like business as usual. This is what everybody thinks. We're just going to go with the current school of thought. Don't rock the boat. There's other cliches you could use there. And then we have what's called the alternative. Sometimes written H sub A or sometimes written H sub 1. And the alternative is the research hypothesis. That's the thing that you're trying to prove. So you would say the Earth is flat. Now, right now, you wouldn't say that's the null hypothesis, but way back in the 1400s, people thought the Earth was flat. Why? Because they'd stand on the beach where water settles, and they'd say, "Oh, look how flat the Earth is. The ocean is flat, and you can obviously tell that it's flat." Well, someone invented telescopes. And about the time of Galileo, I think that happened, and he burned his retinas up by looking at the sun through his telescope. But other people looked at whatever they thought they might want to look at. And in some towns on the coast where they would stand there and look out at the flat Earth, there are ships that go in and out of port. And one day, a ship went out to sea, and somebody had their brand new telescope, and they said, "I'm going to watch this ship go out to sea, and I'm just going to see how small it's just going to get to be this little teeny tiny speck when it gets way out there, and I'm going to see how long I can watch it with my telescope." And maybe their uncle or their cousin or someone was on this boat as a crew member, and so they watched. And what happened as they were watching with their telescope? The boat sank, or at least it appeared to sink very slowly. And so this person with the telescope said, "Hey guys, come look at this. The boat's sinking." And everybody came and looked, and they saw the boat sinking. And the whole town was devastated because they lost a whole crew, fathers, brothers, aunts, uncles. Whoever was on this boat sank. There's no way they could get another boat out there fast enough to help them. And so they had their period of mourning and a mass funeral and memorial services and all that stuff. And they were just getting to the point where they were moving on with life, putting it behind them. And what happens? The boat comes back. It didn't sink. Why didn't it sink? They watched it sink. The Earth's flat, right? Everybody knows the Earth's flat. Well, it turns out that null hypothesis that everybody thinks is true has evidence contrary to it. And that evidence is people watch the boat sink, and then the boat comes back. And if they watch at the right time, they would actually see the boat rise up out of the water. So the alternative hypothesis says that it's not flat. And whatever you mean by not flat, I guess you could say round or whatever. Turns out it's not perfectly round either, because it's a big ball spinning on an axis, so it's kind of looks like a racquetball that's spinning in the air, and it's kind of oblong, just a little bit. But the alternative hypothesis says the null hypothesis is not true, and that's where the burden of proof lies. So until you had your telescope, until you watch these boats go out to sea, no one really thought there was evidence to support the alternative hypothesis. And look at it, it's flat. So why would you conclude otherwise? And so that's what's going on with hypothesis testing in general. We are going to do hypothesis testing for the parameter mu. We're going to say mu is equal to mu 0, or we could use pi. Okay, pi is equal to pi 0. And the alternative hypothesis is going to be that mu is not equal to mu 0, or pi is not equal to pi 0. Now, this is what we call a two-tailed test, and it's possible to have a one-tailed test in which we would say, under the null hypothesis, mu is greater than or equal to mu 0. Under the alternative, mu is less than mu 0. And you could go the other way as well. So this would be a right-tailed test. You have a left-tailed test. Just reverse those things. Okay, so we have a decision to make. Anytime there's a hypothesis, we have to decide if the hypothesis is correct. Or in other words, we have to decide, should we reject the null hypothesis, or should we not reject the null hypothesis? If we reject the null hypothesis, we're saying that it's not true. If we don't reject the null hypothesis, what we're really doing is punting down the field, kicking the can down the road, saying, well, maybe it's true, maybe it's not true. I don't have evidence to reject it, so I'm just going to go with it for now. But that doesn't mean I think it's true necessarily. I'm just not going to reject it. So this sort of thing shows up all over the place. And if you want to think about this in terms of decision making, we have two states of reality. Either H0 is true or H0 is false. Are we ever going to know if H0 is true or false? For sure, 100%? You guys know that the Earth is round? If you go out to space, you can see pictures of it, I guess, and it looks like it's certainly not flat. It appears to be flat. Locally, you might say that it's flat, but yeah, it's round. Yeah. Okay, so we know that it's round. We know that it's not flat. We've rejected that null hypothesis a long time ago, except for someone in the media recently has pontificated about this topic. Anybody know who it is? Kyrie Irving, the pro basketball player. He said something, I don't know exactly what he said, but I'm not so sure he thinks that the Earth is flat, but I think his statements were more about people just jumping on the bandwagon and saying it's one way or the other. Anyway, but we've got a decision to make. We can either reject H0 or do not reject H0. If we reject H0 when it's true, is that a good thing or a bad thing? Null hypothesis is true and we reject it. That's what we call a type 1 error. If the null hypothesis is true and we don't reject it, that's the correct decision. If the null hypothesis is false and we reject it, that's the correct decision. And if the null hypothesis is false and we don't reject it, that's an error, and we call that a type 2 error. So the probability of making a type 1 error is called alpha. And we used alpha when we did confidence intervals. We said 1 minus alpha is our confidence level. Well, that's the same alpha that we're using here. Okay, so that's a link between confidence intervals and hypothesis testing. The probability of a type 2 error is called beta. So alpha, beta, first, second letters in the Greek alphabet go with type 1 and type 2 errors. Be very careful because a type 1 error is not alpha, or alpha is not a type 1 error. Alpha is the probability of a type 1 error. Type 1 error is when you reject. It's the event of rejecting the null hypothesis when it's true. Not alpha, that's the probability of doing that. So if we have null hypothesis to be false and we reject H0, then the probability of doing that is what's called the power, which is 1 minus beta. In other words, it's the probability of making the correct decision when the alternative hypothesis is true. And so the probability of this other correct decision is 1 minus alpha. And what do we call that? That actually does have a name. It should be obvious. It's the confidence level, right? So anytime you're faced with a decision to make, you can think of it in terms of this context. And here's an example. Criminal justice system. What's the current cops and robbers show where they go prosecute and go to court and all that? Used to be Law and Order. Is that one still around? Now they've got like 5 variations on it. Anyway, what happens in the court is somebody is arrested and they're brought before the court and the judge, and before they even get there, the prosecuting attorney says, look, we've got evidence, we think this person committed the crime, we're going to go make that argument. So their job is to convict, is to talk the jury into putting this person in prison, right? That's what their job is. It doesn't get to court unless they think that they've got a case. If there's no evidence, then they're going to acquit, or they're not even going to take it to trial. So the null hypothesis is that the accused person is innocent. And that's what they tell the jury. Look, unless there's very strong evidence beyond a reasonable doubt, then this person is innocent, and the alternative hypothesis is then they're guilty. So we have, if the null hypothesis is true, we have they're innocent. If it's false, say they're guilty. What does it mean to reject the null hypothesis? it means we're going to convict. And if they're not convicted, then they're going to be acquitted. And so the correct decision if somebody's innocent is to acquit. Correct decision if they're guilty is to convict. So what about these other errors? These other off diagonals, or the diagonal here, this is going to be type 1 error and type 2 error. So if somebody's innocent and they go to jail, that's a type 1 error. Is that good? Is that bad? It's bad, right? If people are innocent, they shouldn't go to jail. You know, there's already been some crime committed. It wasn't done by this person. They shouldn't be responsible for it. But what happens when they go to jail? They stop working. They stop paying taxes. They stop taking care of their family. They stop doing all these things that make the world a better place for everybody else. And instead, they now sit around and do whatever it is they do in prison, watch television, read books, lift weights, whatever it is. And so we, people not in prison, are paying for that. So you could, in some ways, measure the cost of a type 1 error. Right? You know, maybe they're not going to reach their full potential now because they're in prison. They don't have access to the resources they need. Maybe it's the next Bill Gates. You know, they're going to do something really big, really exciting, change the world type thing. You can't really measure that. What about a type 2 error? What happens there? Somebody who's guilty is set free. So what's the cost of that error? Well, they're still paying taxes, although if they're guilty, maybe they're criminals and they're not paying taxes anyway. But what if they get the, you know, they get off on a technicality or something? They say, yeah, that was easy. I got off the first time. I'm going to go and commit murder again. And, you know, so the costs are harder maybe there to calculate. But the point is that you don't want to make either of these types of errors. But there's always a chance that you're going to make one of these errors. Alpha is the probability of making a type 1. Beta is the probability of making a type 2. And in statistics, what we're doing with this, alpha and beta are never going to be 0. Okay, so here's another example. Anybody ever buy anything online? Everybody does that now. Where do you go? Amazon. Where else? Anybody ever buy anything on eBay? So back before Amazon was big, eBay was pretty big. Now, no one seems to use that in college anymore. Every time I ask people, they're like, "What? What's eBay?" But eBay, when it first started, was kind of the Wild West, and they wanted you to think the null hypothesis to be that the transaction's legitimate. And so, you know, you go in there and they try to make you feel comfortable that way, but it's not always the case. Somebody has their account hacked. Somebody's posting, you know, stolen items or whatever it is. And so if the null hypothesis is that the transaction's legitimate, what is a type 1 error? Xbox. Anybody play Xbox in here? No? What's the cool thing right now, video game wise? PlayStation? You guys don't play video? No one plays video games in here? You just do the Java applets that I gave you, that I showed you, right? That's more fun anyway. Okay, so the null hypothesis is that it's a legitimate transaction. All right, I'll delve into my own personal experience. When I first came to Drexel, I graduated from college and got my PhD and got a job here at Drexel, and it wasn't, you know, they don't pay tons of money, but it was a lot more money than I've been making. So I said, I need to get a bike. I need a good mountain bike. And I looked on eBay, and there was this Ellsworth Truth. Anybody know about Ellsworth bikes? They're really expensive, like $4,000. This was back in 2003. $4,000, and they were selling it for $600. And I thought, wow, I mean, it wasn't brand new, it was used and whatever. So I thought, I got to have that bike. And so I bought the bike, and I never got the bike, but I paid him $600. Okay, so what's a type? What type of error is that? And again, this was back in the Wild West days, before they had all their policies in place that guarantee return of money and all that stuff, and you get ripped off like that. So what's a type 2 error? Sorry, that's a type. I asked you what type. It's a type 2 error, right? The null hypothesis was false, and I didn't reject it. No, sorry, the null hypothesis was false, and I went with the and I didn't reject it. So that's a type 2 error. So it cost me $600. What's a type 1 error in that situation? If it was a legitimate transaction, I was going to get that $4,000 bike for $600, and I said, wait a second, this is what I should have done, of course, but it seems too good to be true. Probably is too good to be true. So that's a type 1 error. What did the type 1 error cost me? I didn't get the bike, but if I had been determined to buy that bike, and it cost me $4,000 brand new, and I went and spent $4,000 on it, then that error would have cost me $3,400, because I could have gotten the bike for $600. So it's an opportunity cost. I didn't actually go and buy that bike, but anytime you make a decision, you can think of it in terms of this hypothesis testing scenario. If you're going to go out and cross Market Street right there, well, if you are standing on Market Street and cars are going back and forth, you're not going to cross unless you look and it's clear. But eventually you're going to get a signal that says, okay, go ahead and cross. The light's green for the cars, and you should be able to get across safely. And so the null hypothesis is I'm going to get across safely. So are you going to get across safely? Is there a chance that you are not going to get across safely, even though the null hypothesis should be that you're going to get across? So yeah, what scenario is that? Someone's robbing Santander Bank right there, and they've got their getaway car, and they run out and they jump in, and somebody drives, and they don't care who's in the crosswalk. They're just going. Or maybe the manhole cover is missing, and you don't notice that, and you walk and you step and you end up down in the sewers. So what's the type 1 error in that case? The null hypothesis says it's safe to get across. You reject the null hypothesis even though it's true. What does that mean? It means you never get across the street. My mother-in-law, when she was a child, told me a story one time. She was on her way home from school, and her mom had said, don't cross the road if there's a car, if there's cars in the road. And one day she didn't come home from school, and it was like a half an hour later, and her mother came out looking for her and found her on the side of the road, just standing there. And she said, what are you doing? Why have you not come home? And she said, well, there's a car right there. I can't cross the road. And the car was parked. But anyway, so, that's an example of making a type 1 error. It was safe to get across, but she didn't take that opportunity. Okay, a type 2 error, what does that mean in that situation? Okay, you think it's safe. It's not safe, but you go anyway, and then you get run over. So, how often do those things happen? That's the alpha and that's the beta. And we have the opportunity then, if we're testing, say, this null hypothesis, mu is equal to mu 0. Let's do a one-tailed example. What does the alternative hypothesis say here? It says mu is actually less. I'm going to do it the other way. Sorry. The null hypothesis says mu is less than mu 0, so here's mu 0. And the alternative says mu is greater than mu 0. So I'm going to have a rejection region up here that says if you cross that line, this is called a critical value. If you cross that line, then you're in the rejection region. And the area under the curve is alpha. And so this is a good way to think of this. If you cross the line, anybody ever been in a sandbox or a playground and you draw a line in the sand and say you cross that line and there's going to be trouble? If you've never had that happen, probably you've seen it in a movie or on TV or something. Well, what happens when someone crosses the line? They're in trouble, that's right. And what does that mean? What kind of trouble is there? You're going to fight. It's horrible. But you're going to pull hair and spit and punch each other and throw sand in their eyes. And it's not fun, and it's painful, and someone's going to get in trouble. Probably both people are going to get in trouble. They're going to call the police if it's very bad. But minimum, someone from the school or the parents or someone's going to get involved with this, and it's going to be painful. So when you reject the null hypothesis, you're saying someone's crossed the line. The line's being crossed. We have to now reject the null hypothesis, and we have to go in and do something painful. And it might be physically painful, but probably more likely it's going to be monetarily painful and time-consumingly painful. So imagine you've got a company that makes some sort of fasteners like screws or nuts or bolts or something like that. They have a machine that makes these things, and the machine's calibrated to make them to certain specifications. And the null hypothesis is the machine's doing what it's supposed to be doing because you put all sorts of time and effort into putting the machine in place, calibrating it, getting it going, testing, and so forth. And what happens if the null hypothesis is not true? The machine starts producing bolts that are out of spec. That would be the alternative hypothesis. Well, you got to shut down the process. You got to shut down the whole company, and you've got to figure out what's going on. You got to fix it. Well, that takes time, it takes money, and business is not as usual at that point. So if the line gets crossed, you just got to say, okay, we're rejecting the null hypothesis. Does that mean the null hypothesis is not true? No. There's a probability of alpha that you're making a mistake. Okay, so this critical value is determined by alpha, probability of a type 1 error, and the null hypothesis. If you're doing a two-tailed test, instead of one critical value, we have two critical values. So mu 0 is in the middle. We're going to get alpha over 2 and alpha over 2. So we have two rejection regions, two critical values, and that gives us a decision rule that we just go with. We say, okay, that's the decision rule, let's go with that. And we might be making a mistake. In fact, there's an alpha probability that we're going to be making a mistake, and that's what we're going to do. Okay, so let's look at a right-tailed test one more time. So the alternative hypothesis says that mu is actually bigger than mu 0, and we want to know, what does that look like? Or rather, if we wanted to calculate beta, probability of a type 2 error, how would we do that? Well, alpha tells us where the rejection region is. All right, it's on the right tail. If we get a test statistic, the x bar, if that's bigger than mu 0, then that's potentially evidence in favor of the alternative hypothesis. But the question we have to ask ourselves is the difference between what we expect and what we observe, is it big or is it small? And when I say it's big, what I mean is it's crossed the line, right? When you guys were young and you're being crazy and your parents are like, just stop, and a lot of the behavior, a lot of the craziness, they're willing to forgive. But when you cross that line, then it's big. And so the question is whether the difference you see in x bar and mu 0 is big or not. And if it's big, it means it's in the rejection region. It's across the line. Okay, so how do we find the critical value? Critical value is going to be mu 0 plus z sub alpha times sigma over the square root of n. So what we learned about confidence intervals, what was a confidence interval? Confidence interval for mu was x bar plus or minus z times sigma over the square root of n. Right? In a one-tailed test, the critical value is a little bit different, but in the two-tailed test, we have mu 0 plus z sub alpha over 2 times sigma over the square root of n, and mu 0 minus z sub alpha over 2 times sigma over the square root of n. So what's different between that and the confidence interval? The confidence interval is centered at x bar instead of mu 0. So if mu 0 is in the confidence interval, that means x bar is in the non-rejection region. And thereby, confidence intervals and hypothesis testing are the same thing, at least when you have a two-tailed test. Okay, so move that to the previous page. If the alternative hypothesis is true, what does that mean about mu? That means mu is up here somewhere. We'll call it mu 1. Now, it might be in the rejection region. It might not be in the rejection region, but it's definitely bigger than mu 0. So if I said this is the new distribution, then beta is going to be the probability of making a type 2 error. That's the probability of not rejecting when you should reject. So under that blue distribution, we want to know what's the probability of being in the non-rejection region, which means the power of the test is right here, 1 minus beta. So you can't actually calculate the power. Why not? If we knew what mu was, we wouldn't be doing this experiment or this exercise. We don't know what mu is. So the power can be calculated if you assume a value for mu that goes along with the alternative hypothesis. And so what's commonly done is to calculate what's called a power curve, where you say, let's just take a bunch of different values for mu 1 and calculate the power. And then we can determine if the test that we're interested in has, or that we're performing, has enough power to differentiate between the hypothesized value and what might be the real value. And that gets us to a question of statistically significance, or statistically significant differences, or practical differences. So if you have expected value of the amount of money in your bank account, if it's $1,000, is that all that different from $1,020? No, it's not that much different. Do I really care if I can't differentiate between 1,000 and 1,020? Probably not, because practically the differences aren't that big. If I took a big enough sample size, I could have a powerful enough test to distinguish the difference between 1,000 and 1,020. So statistically, they could be significant differences. Practically, might not be. So you have to look at that and consider that. And yeah, so I want to actually do a hypothesis test with you guys. And here's the null hypothesis. My null hypothesis is that you guys are psychic. Sorry, that's not the null. The null is that you guys are not psychic. Okay, so does it make sense why I would use that as my null hypothesis? What is it I'm really trying to get to? I'm trying to determine if you are psychic. Right? That's my alternative hypothesis. Okay, so if the null hypothesis says you're not psychic, that kind of goes along with what most people think. You know, I don't feel psychic. You know, if you ask me a question, ask me to guess what you're thinking, I don't think I can do that. And the alternative then would be what we're trying to prove. So the burden of proof is on the alternative hypothesis. So how could I test this? What kind of statistical measure could I use in order to test this hypothesis that you're psychic? Okay, so I could select some numbers, random numbers, and ask you guys to guess. Didn't we do that already in class? Guess the secret serial number? No one got it right. So I guess I could use that as evidence to say you're not psychic. I'll go with the null hypothesis. But we didn't really quantify that. We need actual hard numbers in order to say, did we reject or not reject? Right? We want to draw a picture and say, look, here's the rejection region. There's the line in the sand. If we cross that line, then we're going to reject the null hypothesis. And that's where it gets painful, because then we have to tell people, hey, I'm psychic. You have to write home and tell your parents, hey, I'm psychic. My statistics class is psychic. And then, I mean, that's only if you want to broadcast that. You don't have to, of course. But what are people going to say when you tell them that? Yeah, go ahead. They're going to say, prove it, okay. Or they're going to laugh at you and say, oh, no, you're not. And anyway, it can be painful. So let's devise an experiment. Here's an idea. Here are three numbers, 1, 2, 3, and 4. And in a minute, I'm going to blank my computer screen so you can't see it. And I'm going to erase 3 of these numbers. Okay, now this is not like the pick-over guy that swapped out the cards on us. So this is not that psychic experiment. This is a different one. One of those 4 numbers is going to be here. Okay? And once I do that, I'm going to ask you guys to read my mind. And I'm just going to, whichever one's left there, I'm going to just think about it, and then you guys are going to tell me what number you think is left there. Okay? Does that make sense? So that's the experiment. All right. Let me just pull up, make sure. Okay. So when I start this poll, you're going to have options A, B, C, and D, and those are the only things that you can select. And so it's going to be one of those numbers. Okay? All right. This is exciting. Isn't this exciting? This is fun. You guys are all happy about this, right? Okay, so, and again, no funny business here. Nobody saw what I just did, right? You all closed your eyes and, okay, so I'm thinking of the number, and you're not going to see what everybody else is saying, so we don't have that bias showing up either. And I'm totally thinking of this number. And I think I just counted 25 of you guys, so if that threw you off while I was counting, I wasn't thinking of that number, except for once, because I said that number in my head, whatever it might have been. So let me think about it again while the 10 remaining people that have not answered put their answer in. I need everybody's answer on this. It's mission critical. All we've got is 18 so far. 19. 6 more of you guys. 20. I don't mean to put pressure on you, but if you're not feeling the vibe, just go ahead and do your best on this. The 5 of you that is still not answered. Is that all we're getting? Okay, well, we'll stop it here. Now I'm going to turn, I'm going to deactivate the poll so that you can't see what the answer is, and then answer. So again, this is your last chance. Count of 10. Okay. That's the number I was thinking. And so what does this mean? How are we going to use this to determine if you guys are psychic? What are we going to do? If the null hypothesis is true, which says you're not psychic, what proportion of you should get this right? Really low, okay. What exactly though? There are 4 options, so it should be 1/4. So we'll just write that down. 0.25 is our hypothesized value under the null hypothesis. What should the alternative hypothesis be? Pi has some relationship to 25. I'm going to say it's bigger than 25%, which really means my null hypothesis is that mu is less than or equal to 25%. We're going to treat it as if it's equal, but if our results come back and we have less than 25%, then that doesn't suggest you're psychic. All right, so we're really only interested in what's going on here if we have pi greater than 25%. So the sample proportion P is x divided by n, and that is what kind of distribution? Using the central limit theorem, we know that this is going to be normal with a mean of 0.25 if the null hypothesis is true, and a standard deviation of 0.25 times 1 minus 0.25 divided by n. In this case, n is 20. So that's the distribution if h0 is true. Now I'm going to move this 3 up to here so draw a little bit better. So if the null hypothesis is true, what do we have? 0.25 is the mean. And I'm going to then look at the result and say, is the difference that I observe due to randomness because it's a small difference, or is it due to the null hypothesis being false because there's a big difference? In other words, there's going to be a rejection region. If we say alpha is 5%, this rejection region will start at 0.25 plus 1.645 times the square root of 0.25 times 1 minus 0.25 over 20. Okay, so what's that value? What's that number? Let's come over here and plug it in. We have n is our sample size. Alpha is going to be 5%. Our z sub alpha. And what else do we have? P. So we have pi. So n in this case is 20. Alpha is 5%. Z sub alpha, that's the value that has 5% of the area to the right of it, which means there's 95% of the area to the left of it. So we get that by norm dot s dot inverse 1 minus alpha. That's where we get the 1.645. Our pi value is 0.25. So the margin of error, let's just write it out. Our critical value is going to be equal to pi plus z times the square root of pi times 1 minus pi divided by n. So the critical value is basically 41%. So 0.409. So this is my rejection region at the alpha equals 5% level. If I see bigger than 40%, then I'm going to reject null hypothesis. So bigger than 41%. So what do I have? 20. So if I see more than 8 people who said 3, that's going to be evidence. So 9 and above, that's going to be evidence in favor of the alternative hypothesis. Okay, are you guys just dying with curiosity now? Yes. Are you? Okay, good. All right, check it out. Drum roll. Whoa! Holy cow! Are you kidding me? You got to be kidding me. This had to be contrived somehow, didn't it? You guys were oh my goodness. Okay, so what's the actual value? It's not exactly 65%. Let's look at the count here. So we have 13 out of 20. Where if the null hypothesis were true, we would expect how many out of 20? 25% would be 4, and we saw 13. So P in this case is 13 out of 20. So let's come over here and plug this in. Here we have x, and here we already have n. So x was 13. So P, the sample proportion, is equal to x divided by n. And we get 65%. Okay. So where does that lie? Is that in the rejection region? Yeah, it's like right here, 0.65. So what does that mean? Is the difference between 25% and 65 practically significant? Yeah, that's a big difference, 40 percentage points. Okay, is it statistically significant, the difference? Yeah, it is. Why? How do we know that? Because it's in the rejection region. So when we say statistically significant, we mean the result is in the rejection region. So that means we can't just attribute the difference between 25 and 65 to randomness. In fact, we'll see that another measure we can use is something called the p-value. And that's another way to do hypothesis testing. If we take the p-value approach, that says find the area under the curve further out in the tail than what we observed and compare that to alpha. So we have two ways to do this. The first one says the critical value is, in this case, less than the test statistic. We'll call it the p-stat. Or the other way to do it is the alpha level, or alpha, is greater than the p-value. So if the p-value is less than alpha, that means reject the null hypothesis. And there's this cute little song or mnemonic you can use that goes, if the p-value is low, H0 must go. Get that? See it rhymes there? If the p-value is low, H0 must go. So when you're going to sleep tonight, Just think about that. P-value. Say it in your head a few times. Say it out loud. That'd be even better. Your roommates might think you're weird, but that's okay. If the p-value is low, H0 must go. So I can compare the p-value to alpha, and if it's less than alpha, that means we're in the rejection region. So I don't actually have to calculate this test statistic, or sorry, the critical value if I don't want to. I can use the p-value approach instead, and that's actually what's probably more useful, because if I report the p-value, then you can choose your own alpha level. You don't have to use my alpha level. If I use a critical value approach, then I'm saying here's alpha, and you have to use my alpha. And you know, people don't always agree on alpha. So what's the p-value then? Well, let me ask you first of all, do you think you could find that p-value? Could you find the probability being bigger than 65% in this scenario? Is that something we've done in class so far? Yes, it is. This is just a normal distribution. We know what the mean is, we know what the standard deviation is, and we know what the region is that we're interested in. Yeah.
How can you assume normal?
How can we assume normal?
Because it's less than 30.
So the assumption you're talking about is not for proportions, but for means. So the central limit theorem actually does kick in here. I believe the textbook says if n times pi and n times 1 minus pi are greater than or equal to 5, then you can use the normal on this. And so in this case, when we're saying pi is, or p is the proportion that are 3, we're saying the rest are combined together and not 3. So we have 13 successes, 7 failures. So the normal distribution can be used here for proportions. So that's a good question. Good point to think of. Okay, so let's come over here and find what's the probability. First of all, I'm going to find the z-score. Z-score. What's the z-score? The z-score is going to be the distance, the standardized distance between what we observe, so p, and what we expect, which is pi. And to standardize that, we have to divide by the square root of pi times 1 minus pi divided by a2, which is n. So our z value is 4.13. So what does that mean? That's 4.13 standard deviations above the mean. All right, so if we put this in the z world, so this is p, that's z. Is 4.13 big or small? For standard deviations, that's big. It's really big. Think of the empirical rule. That tells us that 99.7% of the data is within plus or minus 3 standard deviations. So we're going out even further than that. In fact, the normal z table in the textbook only goes up to 3.5, I think, or maybe it's 3.9, 3.8. It doesn't even go this high. So the p-value is going to be extremely small, and it's going to be 1 minus norm.s.dist. Put the z value in. Actually, p-value is going to be 1 minus norm.s.dist z, comma 1. So there you have it. P-value is 1.8 times 10 to the minus 5. So that's a decimal place, 4 zeros, and then a 1. So that's pretty rare. That's pretty small probability. But that's how we measure how likely the null hypothesis is given the observation, the data that we observed. Okay, so What are you going to tell your parents tonight? Are you psychic? Well, 65% of you got it right. So I don't know, does that mean that 65% of you are psychic? Does that mean that there's some sort of group, collective intelligence that we've hit upon somehow? There's a really interesting study that came out not too long ago about people trying to guess the weight of a steer at the county fair, and they found that nobody got it right or was even that close. But if they average over all the guesses, the average guess is really pretty close, like within 1%. And so there is some argument that can be made for the collective intelligence or collective wisdom or knowledge of groups. So did we just happen upon that somehow? No, we didn't. Are you guys really psychic? No, you're not. How did I know to pick the number 3? By the way, it's always 3 that I use. My class earlier this morning, guess what the percentage was? We had 23 people, 70%. Got it right. Cognitive bias, is that what you said? Okay, could be. Somebody at some point did a bunch of experiments and said, what number do people think of most often when they're choosing between 1 and 4? And it's 3. And I wasn't even thinking about the number 3 when I told you I was. I was thinking about going skiing and then kayaking and then skiing again and then rock climbing and lots of other stuff. But I was definitely not thinking about the number 3. So that's a good illustration of what can go wrong when you do a hypothesis test, because it looks pretty cut and dry here, doesn't it? We set up this experiment, we collected data, we did all that with pure intent and good faith in the scientific process that we have here, but it's wrong. So you got to be able and willing to be able to kind of dig deeper and look at the results and say, wow, 4 standard deviations, that's pretty amazing. There's got to be something else going on here, maybe. You got to be willing to dig deeper, is what I'm saying. So I'm pretty sure you're not psychic. I mean, I can't rule it out completely, but I'm pretty sure you're not. So questions, thoughts, comments? Wasn't that fun? You guys came to class and for a few brief moments you thought you were psychic, and it turns out you're not. Sorry to bring you up so high and then dash you down on the rocks. Okay, well, I'm going to entertain homework questions. Homework 6, and then we will be done whatever time you guys, whatever time we get through these questions. And if you want to stand up and stretch your legs or whatever for a couple minutes, feel free to do that. But you all don't look like you want to take a break, so we'll take a break at the end of class. How's that sound? You guys good with that? Everyone's good with that? Okay. Has anybody tried homework number 6 yet? It's due on Thursday night. Quiz number 6 is due on Friday night. We have homework 7 and quiz 7 next week, and the following week there's just homework 8, no quiz 8, and that's week 10. And I think the final exam's been scheduled for Tuesday, and I don't know the exact times, but it will be in G Hall, and it will be in computer labs. I've got 2 computer labs, so it should be similar to the midterm exam.
So it will be like Excel, like we did in right?
Yes, but from what I understand, the Excel functions are going to be all working by then. And if they're not, we'll sort that out when we get there. Okay, so homework number 6. Do you want me to pick a couple of problems to go over? Okay. I'll do that just because I don't want to let you out of class like an hour early. Although, maybe I do want to let you out of class. All right, let's look at number 14 and number 16 and number 5. And let's go ahead and start with number 5. All right, fuel economy for this Lexus car with all those specs is a normal random variable with mu is equal to 24.5 and standard deviation of 3.5. So they tell us what mu and sigma are. That's a good hint that we're going to be using a normal distribution on this one. Let me just show you problem number 1 really quickly. This one is not normal. I mean, it's normal, but it says a random sample of 23 lunch orders has a mean bill of 12.8 and a standard deviation of 4.66. So on this question, this standard deviation is from the sample. It's not the population standard deviation. So it's S, which means you're going to use a T instead of a Z. But for number 5, we are told that we have a normal distribution, and they tell us the mean and the standard deviation. So the first part says, what's the standard error of X bar? So this is number 5. X bar is going to be normal with mean mu. What's the standard deviation? Sigma over the square root of n. What's the difference between the standard error and the standard deviation of X bar? Nothing. They're the same thing. So if they say standard error, usually they're talking about the standard deviation of some estimator. So X bar is the estimator. Standard error is just going to be sigma over the square root of n. And so we have 3.5 and a sample size 9. So this is going to be 3.5 divided by 3. Or rather, divided by square root of 9. Part B says, within what interval would you expect the sample mean to fall with 95% probability? So we have a mean of 24.5, and we're saying this interval has 95% of the area between it, which means how much is to the right? 2.5%. How much is to the left? 2.5%. So that means we have 25.4 plus 1.96 times sigma, which is 3.5, divided by the square root of 9. That's the upper value. The lower one's going to be minus 4.5 minus 1.96 times 3.5 over square root of 9. Okay, so let's see. Let's go over to Excel. So this is homework 6.5. And what do we have here? Mu, sigma, n, alpha, z sub alpha. Let's just plug these things in. We have 24.5, 3.59, alpha is 0.05, z sub alpha is equal to norm dot s dot inverse 1 minus alpha over 2. We get the 1.96. You can either use Excel or look that up in the chart in the book, or if you have a TI 83 or 84 calculator, something like that, you can look it up on that. And so what do we want here? We want an interval that has 95% in the middle. So we said this is, we'll say this is the lower and upper. So for the lower, we're going to get mu minus z times sigma over the square root of n, 22.21. And to get the upper, you just do the same thing, except for instead of minus, you say plus. Let's just check this out. See if we got it right. Now we'll come back in a minute. All right, so let's look at number 14. Okay, so we got that right. Again, to get the upper version, upper value, just put plus instead of minus the z. Number 14 says find the margin of error for a poll assuming 95% confidence and that pi is equal to 0.7. So for 14, we say pi is equal to 0.7. We have alpha is equal to 0.05. What do we want? The margin of error. So what are you talking about, margin of error? We want a confidence interval for pi, which is going to be p plus or minus square root of pi times 1 minus pi over n times z. And this is kind of dumb. If you look at the confidence interval, it has pi in it, but we don't know what pi is. That's what we're trying to estimate. So in this case, they're telling us what pi is. So if we knew what pi was, why would we do this? But it turns out this is just a guess. Now, if I didn't know what pi was and I didn't know what I should use for the guess, I could just put p in there. So p times 1 minus p is an estimate for pi. But for this part, the margin of error is that. So the confidence interval is p plus or minus the margin of error. So the margin of error is going to be z, so alpha over 2 times the square root of pi times 1 minus pi over n. Plug the numbers in, we get 1.96 times the square root of 0.7 times 1 minus 0.7 over n. And what's n? 60 in this case. So for part A, n equals 60. So let's come back over here and try to type in all that. So let's copy it, paste it in here. So this is homework 6.14, and I have n, which in this case is 60. Alpha is 5%. This is z sub alpha. I actually want z sub alpha over 2. So I'm going to change that. Divide by 2. So there's the 1.96. Now pi, we're told, is 0.7. And so the margin of error is just going to be z times that thing. The margin of error is z times the square root of pi times 1 minus pi divided by n. The margin of error is about 11.5%. And that's just what we're adding and subtracting. So to do the other parts, all you do is change the values of n. So 2400 or 240, 240. And you can copy and paste all this if you want. 60, 240, 600, 2400, I think. And the point here is that as you get bigger and bigger sample sizes, look what that does to the margin of error. The margin of error drops smaller and smaller and smaller. And you can also play around with pi. If you had 50% instead of 70%, you can see the margin of error is going to be a little bit bigger. And why is that? Why does it get bigger if you put in 0.5? This is one of the other questions is not really clear. We'll see. Maybe it's the next one we're going to look at. It's this one here, 50. Nope. Number 3. Okay, so for problem number 3, you're told that you have a pole of a certain size, 2,237, and you want the margin of error with a confidence level of 95%. But you'll notice it does not say in here what to use for pi. So if you go to do this calculation, which is basically all you're being asked to do in that question. In fact, just throw this in here. Homework 6.3. We have n in this case is 2237. Alpha is still 5%. And so they want the margin of error, but they don't tell us what to use for pi. So if it doesn't tell you what to use for pi, what should you use? 50%. Put 0.5 in, so that's what we're going to use to calculate the standard deviation. Okay, so come back here. If they don't tell you anything to use for pi and you haven't taken a sample yet, use 50%. So question number 3, use 50%. Why is that? Because this function, pi times 1 minus pi over n, if I wanted to maximize this, I would say this point here at 0.5, this is pi times 1 minus pi, and there's a constant in there and whatever, but this part's going to be maximized because it's a parabola at 0.5. So this has zeros at 0 and 1, so here's 1 and here's 0. So the best case or worst case scenario would be when you have pi equal to 0.5. So change that to 0.5, and it gives you the plus or minus 2% that you see quite often, actually. Okay, so let's look at this last question then. City fuel economy of that car is a normal distribution with a range from 16 miles per gallon to 21 miles per gallon. So part A says estimate the standard deviation using method 3, the empirical rule for the normal distribution. I believe that was a question on the exam, wasn't it? Something like that anyway. So the range is equal to the max minus the min. In this case, the max is 21, the min is 12. So the range is equal, did I get that right? 16. So the difference is 5, and the empirical rule says almost all the data is within plus or minus 3 standard deviations. So plus or minus 3 is 6 standard deviations. So the range is about equal to 6 times sigma, which means sigma is equal to the range over over 6. So in this case, we get 5 over 6 is our estimate for sigma. So that's what we're asking for part A. Part B says, what sample size is needed to estimate the mean with 90% confidence interval, 90% confidence and an error of plus or minus 0.25. So part B says, using this estimate for sigma, we want the margin of error to be equal to 0.25. What's the margin of error in this case? We're talking about the mean. So we have z, so alpha over 2, times sigma over the square root of n. Now this question is actually asking us for n, not for sigma or z. So we're going to solve for n, and we get n is equal to z times sigma over the margin of error and square that. So I'll plug in my numbers. 1.9, what's my 90%? So it's 90%, it's not 1.96, it's 1.645 times 5 over 6 divided by 0.25. And we square all that. Let's come over here. So n, that's what we're looking for. We have alpha. We have the margin of error. What else do we need? Sigma. So the z value. And so let's plug these things in. Alpha is 10%, margin of error is 0.25. Sigma is 5 divided by 6. Change that back to a number. And so this is going to be equal to, the z value is going to be norm dot s dot inverse 1 minus alpha over 2, 1.645. So n is going to be equal to the quantity z times sigma divided by margin of error, square all that, and we get 30.06. Now you might think you should round that down to 30, but you actually want to round it up. So notice if I round it up, I get it right. If I round it down, I get it wrong. Why is that? Why do you think? Well, I can't have a fraction of a sample, first of all. But if I round it down, then I'm not going to have the margin of error that I want at that significance level. So I'm going to actually get something bigger, or sorry, my margin of error is actually going to be smaller. It's going to be better, but I have to pay for that by an additional sample. Okay. So questions, comments? Nope. Okay, we'll see you a week from today then.